Today we study scalar particle. Until now we have studied electromagnetic interaction for the non-relativistic particle. So we have introduced covariant derivative and implemented the covariant derivative into Schrödinger equation. So let us try to find the equation of motion for scalar particle that does not have any spin. The scalar particle electromagnetic interaction can be studied by using complex scalar field. But before we go ahead, we just consider a neutral particle. Free particle with the charge, with the no charge, can be explained using the Hamiltonian. This Hamiltonian can be squared to have this kind of form. And why don't we construct a wave equation that satisfies this relativistic equation for energy? The Hamiltonian is to be replaced with the IH bar partial time derivative, and momentum is replaced by h bar over I gradient. And in order to construct a relativistically covariant form, it's better to multiply speed of light to make the time dimension to have the length dimension. So I have multiplied the speed of light and divided by speed of light. We substitute this Hamiltonian and momentum operator to this equation and substitute the wave function. Usually it is conventional to use a phi for the scalar wave function. So if we square this guy, we have minus h bar squared c squared and double time derivative and scalar wave function, and mass term is here and momentum is replaced with h bar squared c squared. We find we have common factor h bar squared c squared. So why don't we move this term to the right hand side and flip the left and right? The overall factor is h bar squared c squared and time derivative subtracted by spatial derivative. So this is four-dimensional object, the scalar object, round mu. And because we have pulled this h bar squared c squared out, the mass term becomes m squared c squared. It used to be m squared c to the fourth, m squared c squared divided by h bar squared. So we just remove this over factor h bar squared c squared to find this equation. And it is this guy is sometimes written as around squared. So this equation is called the Klein-Gordon equation that describes the motion of a scalar particle. If we want to introduce the electromagnetic interaction, we learned that we have to replace the derivative, usual covariant derivative, with gauge covariant derivative. Actually, that is a complex. We remember round mu is replaced by round mu plus I q over h bar c a mu, something like that. Right. But if phi is real, then we have some problem. So we will find that one after we consider the complex case. So before we go ahead, we just want to construct the Lagrangian density function that produces this Klein-Gordon equation as Euler-Lagrange equation. So Euler-Lagrange equation for this scalar particle is written like that, and the first term should be the same as this first term, and the second term seems to be the same as this term because we have derivative outside and it is square. So inside that is conjugate momentum. Conjugate momentum seems to be round mu phi, something like that. Okay, round squared phi can be round mu phi, and this seems to be the momentum, conjugate momentum. So we solve this partial differential equation to find that multiply this guy here, and it is a squared, a kind of squared form. So I have 1/2 round mu phi, round phi, and this integral does not is related to the partial derivative of phi. So there is some constant term that is independent of the derivative of phi. That can be solved by using second constraint. The second constraint is minus derivative of phi is equal to this term. So let me copy this one, and this is the same as this. And then until now we have found that Lagrangian is the sum of these two terms, but if I take the derivative with respect to phi only, this kinetic term disappears. So it seems to be this guy is just negative partial derivative of phi f function with respect to phi. So if we integrate both sides, then we find the 1/2 minus over a factor m squared c squared over h bar squared phi squared. Okay, substitute this one in here to find the final result for the Lagrangian density function for the scalar particle. Previously, I commented that if we replace the covariant derivative with the gauge covariant derivative, we will have some problem because phi should be complex. So why don't we introduce two real scalar fields that satisfy the same Klein-Gordon equation with the same mass? Okay, so if I have two fields as a linear combination, square root of 1 over square root of 2 phi 1 plus I phi 2, and phi 1 and phi 2 are both real, and both has the same, both are satisfying the same Klein-Gordon equation with the same mass m. These two differential equations can be added after multiplying I, or subtracted to find that phi and phi star, phi and phi star, phi and phi star is minus I. Okay? So these two equations are equivalent to these two equations. Anyway, because we have introduced two fields and they are independent, so Lagrangian can be additive. Okay? So if we add these two, the final result is just copy the original result for a real scalar field twice for phi 1 and phi 2. And we know from complex variable 1/2 phi 1 squared plus phi 2 squared can be decomposed into the product of two complex numbers, 1 over square root of 2 phi 1 minus I phi 2, and 1 over square root of 2 phi 1 plus I phi 2. And this is phi star, and this is phi. So this guy is actually phi star phi. So this one can be replaced 1/2. This guy can be expressed as a phi star phi. In the same way, the kinetic term of the both fields can be expressed as a round mu phi star, round mu phi. As a result, if we have a complex scalar field that is composed of two real scalar fields with the same mass, then the Lagrangian density function becomes like that. By making use of this result, let us consider the electromagnetic interaction of the scalar particle.